Hi, I'm J.Xu, PhD student from the Ohio State University. I will be presenting our work, KeywordMap, Attention-Based Visual Exploration for Keyword Analysis. This work is from the Graphics and Visualization Study Research Group in the Ohio State University. Given large collections of documents, filtering through it and identifying useful information is very time-consuming. So keyword analysis becomes essential and important. They can be regarded as a compact representation of documents for depicting their essential ideas. It has been used for document categorization, summarization, and indexing. One of the widely used methods for keyword analysis is topic modeling. Given a large collection of documents, users need to decide the number of topics as hyperparameter. So the algorithm will treat the documents as bag of words to generate the topics based on statistical computation. Finally, it will return topics with word distributions. However, there remain some challenges. First, in the result, it doesn't provide the relationship among words, so why certain words are placed together is not always clear. Second, it's hard to know the number of topics without prior knowledge. In summary, there are several problems. First, using bag-of-words model will lose the context information. For example, the word bank has different meanings given the context. So how to use the context information properly is the first challenge. Second, how to decide which word is keyword and find the correlated ones as a concept is not easy. Third, the number of topics doesn't have ground truth in most cases, so how to identify the topics is not trivial. We propose a systematic method to solve the three challenges. First, we attempt to capture the word relationships in network instead of treating them independently. We propose to utilize the attention mechanism to model the word relationships in the language model. For the second problem, based on the word network, we propose an algorithm to rank the words, considering how influential each word is in the network. Lastly, we develop an interactive system, KeywordMap, to analyze the word network in an efficient way. We introduce the first component, building attention-based word network. Constructing a network from corpus can be divided into two steps. First is a domain-driven attention tuning process, and then is the construction of S network. Before we explain our model, we would like to give some background knowledge. Transformer is a very popular architecture designed to translating one sequence to another sequence. It has two components. Encoding components consist of layered encoders, which converts the input to embeddings through each layer. Similarly, decoding component translates the embeddings back into another sequence layer by layer. The pre-trained language model only contains the encoding component because the generated embeddings can be further fine-tuned on downstream tasks. So in this paper, we only focus on the encoder part. Now let's look at the structure of each encoder. First, the input sentences are converted to word embeddings. Then the embeddings go through a self-attention layer and a feed-forward layer. The self-attention layer generates the new embeddings as a function of all the context words. The computation is processed in three steps. First, each input vector is multiplied by some learnable parameters to generate three embeddings: the query vector, key vector, and value vector. Suppose now we compute the contextualized embedding for word I. We take the dot product of its query vector with key vectors of all the other words. Then the score is divided by the square root of dimension of key vector. Then it goes through the softmax operation. Now we have three softmax values indicating how much attention the word I pays to all the other words, including itself. Lastly, we multiply each softmax value with corresponding v-vector and sum all vectors together. So the final vector is a new embeddings for word I, considering the influences from all the others. So in practice, the process is done by matrix operation for efficiency. So in this step, we have a n by n matrix called attention map, indicating how each word interacts with all the others. So in our method, the process is we put one sentence with n tokens into the encoder. The output is an embedding. We extract the intermediate result, n by n attention map. Each row implied how the word hands out its attention to all the others. Each column illustrates how each word receives attention from others. However, the pre-trained model doesn't capture the domain-specific knowledge, so we propose the domain-driven attention tuning. After the tuning, based on the better performance of the embedding, we can infer the attention map is also improved. Next, we use an example to illustrate the construction of S network. Suppose we have two attention maps for two sentences. Each can be visualized as a directed network. We need to merge them for a consolidated one. We add the first network and initialize two attributes for each edge, frequency and sum. Then for the second network, we check each edge whether it exists or not. If it exists, we add one frequency and sum the attention weights together. So the same thing happens for edge AB. Next, we check the edge BD. It does not exist, so we add a new edge and initialize its attributes. We do the same thing for edge DB, AD, and DA. After we merge all the matrices, we compute another attribute for each edge, weight, by dividing sum to frequency. Lastly, to avoid biased bidirectional edge weights, we normalize weights for pairwise relation. Next, I will introduce our second component, attention-based word influence algorithm. So in social networks, to decide which user is more influential has been an active research topic. Romero proposed a model which argues that besides the number of followers, we should also take follower status into consideration. We find the analogy between social network and S network. So we define the influence score to measure the importance of words by considering the three effects into consideration. Next, I will introduce our interactive system, KeywordMap. It consists of four components. Projection view provides an overview of keywords. Users are allowed to select dataset, part of speech, the number of top keywords with highest influence score, and other parameters. Then they can brush the keywords, which will update the network view accordingly. It reveals the relationships among brushed words. User can filter unimportant edges or add stop words to edit the network. After that, they click the button. Then we perform community detection on the fixed network. The result is shown in the community view. For each word, we measure three different attributes: influence score, TF-IDF, and centrality, and embed the information into the designed glyph. Users are allowed to click any words they are interested in to retrieve the original documents in the exploration view. They can further filter documents based on the specific word relations and also see the details of the documents. This is the whole process of our paper. Our evaluation follows the same order. First, we prove how the domain-driven attention tuning improves the embedding and attention map. Then, we compute the S network with co-occurrence matrix to show its usefulness. Later, to evaluate the performance of our method to extract keywords, we compare it with popular method, TextRank. Last, we conducted case study to demonstrate the effectiveness of KeywordMap. Before we start the evaluation, we would like to provide some tuning details. We have three datasets: BizPub data, news data, and archive data. For the news data, we pre-select 6 topics. For the archive data, we pre-select 3 topics in the computer science literature. For each dataset, we train 2 language models, BERT and XLNet. All the hyperparameters and the training results are shown in the tables. For this evaluation, we use a news dataset. Like introduced before, we pre-select 6 topics. For each topic, we choose 4 words with high frequency and sample 20 sentences for each word. Therefore, we have 80 dots for each topic in the scatter plot, where each dot represents a word embedding. We use different colors to show different topics. Left is a result from pre-trained BERT. Right is from our fine-tuned model. We can see that there is a clear boundary among different groups after the fine-tuning process. We also want to verify the formation of clear clusters in the high-dimensional space. So for each topic, we compute the ratio of pairwise in-class distance to across-class distance. Smaller value means greater difference between the 2 different distances, indicating more clear boundaries. From the figure, we can see that the ratio decreases after fine-tuning, which can be explained by the formation of clusters. Also, we can see that the distance of BERT is smaller than the XFNet, which means BERT can generate more clear clusters than XLNet in high-dimensional space. Instead of the evaluation of final output embedding, we would like to show how the attention map changes as a result of embedding improvements. We randomly pick 2 sample sentences and compute the average attention maps. It's clear to see that in the pre-trained model, each token gives high attention weights to itself, while in the tuned model, each token will not only focus on itself, but also refers to some other relevant tokens. This pattern shows it's more likely to capture the interpretable linguistic information for language understanding. In our method, we combine each individual attention matrix into a consolidated one. So we also want to validate the patterns of the consolidated S network. So first we convert the S network to matrix, and then we normalize each row to the sum of 1. Then we calculate the information entropy of each row, which measures the uncertainty of the attention weights sent out by a token. We expect the entropy will be higher in the fine-tuned model because each token will attend more to others with the knowledge instead of always giving high attention to itself. From the figure, we can see fine-tuned models have higher entropy values, which also confirms our hypothesis. The co-occurrence matrix is one of the more popular methods to capture word relationships by computing how many times the 2 words are co-occurring in a sliding window. We compare it with our S network. From the table, we can see there is no big difference with top 3 keywords. However, starting from rank 4, co-occurrence matrix grabs general concepts like method, analysis, but the S network can retrieve some informative keywords we highlighted in red. We also compare the HW.Shen algorithm with another keyword extraction algorithm, TextRank. It is a very popular method based on Google's PageRank algorithm. We use normalized discounted cumulative gain to measure the performance of output keywords ranking with the ground truth ranking. It is in the range of 0 to 1. 1 means perfect ranking that is the same as ground truth. Compared to TextRank, our method has a higher value with both language models. In our method, there are 2 places requiring hyperparameters. The first one is choosing which pre-trained language model to use, BERT or XLNet. There are 12 identical encoders stacked in the model. The second parameter is whether to extract the attention map from the last encoder or averaging over all encoders. So from the table, we conclude that all layer is more likely to extract some general keywords, such as model, system, algorithm, while last layer can extract some specific domain-related keywords, such as network, graph. We infer the reason is that the last layer grabs more task-specific features that can improve the classification task, but earlier layers can capture some fundamental features. We illustrate how we conducted the case study using KeywordMap with our user, Selena. We use archive dataset from 3 sub-areas in the compute science: data structure and algorithm, computation and language, and compute vision. To begin with some general concepts, she moves the slider to select top 150 nodes in the projection view. The color is predefined by K-means algorithm to determine the possible clusters from distance. To determine whether the closed words are relevant, Selena brushes the nodes with the same colors to show some detailed local structure. So from the network view, she can correlate each cluster to the sub-area. For example, the blue one is related to the computation and language, because you can see lexical, linguistic, sentence are related to the linguistic language. While for the orange one, it is related to the data structure and algorithm, because graph, sequence, text, tree refer to different types of data structure, and the word algorithm also echoes the sub-area name. So she is very positive that the word embeddings are good enough to capture domain-specific semantic meanings in the projection view. Selena proceeded with the green dots, compute vision area. So she clicks the Fix Graph button to update the community view. As shown in this figure, she identified one community. The most important word is image, which shares many links with others. She further confirms these links are also meaningful. For example, the depth and texture are 2 features of image, while image segmentation is a compute vision task to separate pixels into parts. She clicks the word segment, and the exploration can retrieve lots of segmentation-related documents. Further, she filters the documents of interest by selecting the specific keyword relationships between segment and semantic. She receives some text related to semantic segmentation, which is one of the categories in computer vision segmentation tasks, which can be seen in the figure B. So in another community, there are some dominant words which are also related to the essential topics in computer vision, such as recognition, speech, vision. She also confirms the link between speech and vision comes from some interesting research ideas. In conclusion, first, we propose to employ attention mechanism to capture word relationships and domain-driven attention tuning method to incorporate domain-specific knowledge. Second, inspired by a social network model, an attention-based word influence algorithm is presented to compute the word's importance. Third, we evaluate the performance of our algorithm in both quantitative and qualitative manners. Furthermore, by carefully designing the requirements and tasks, we implement an interactive system, KeywordMap, for users to analyze keywords and perform information retrieval. Thanks for your listening, and we're ready for any questions.